Good afternoon. Good afternoon, and welcome to the Concrete Institute Australia. I'm John Nichols. It's my pleasure to be your host for this afternoon's webinar on NEXGen digital innovations in asset management. This webinar invites two young professional members from our NEXGen group to explore and develop topics of interest to them. The speakers are Mihaly Rutkai, speaking on structural health monitoring, and Aden Petersen, speaking on digital innovation in infrastructure. Our first speaker is Mihaly Rutkai. A few words about Mihaly. Mihaly has 8 years of professional engineering experience covering both contracting and consulting in the building sector. Mihaly has strong technical consulting and project management skills and in-depth knowledge of structure condition, durability assessments, and reinforced concrete, structural steel, timber, and masonry design. Ladies and gentlemen, please extend a very warm welcome to Mihaly Rutkai.
Okay, it's getting control. Thank you, John. Beautiful. Thank you, John. I would like to give a little bit of extra detail about myself before proceeding. So I'm a durability engineer at BCRC, and I've been for the past 4 years. Prior to work at BCRC, I have some site experience in construction labouring as well as project management. As during my studies, I combined it with work, and it showed me many aspects of asset management. Now, when it comes to digital innovations in asset management, one key aspect really sticks out to me the most, and that is structural health monitoring. Just as leaps in technology help us in everyday life, so do they keep improving the prospects of structural health monitoring. In this presentation, I will go over what it is, why it is important, its main applications, a few of the methods for structural health monitoring, as well as some real-life experiences and examples. Apologies. So, what is structural health monitoring? Well, it's a process of continually assessing the condition and performance of structures such as buildings, bridges, and other critical infrastructure. It involves using sensors and data collected to detect changes or damage to a structure over time. These methods often involve sensors that monitor vibration, displacement, and temperature, among other factors. Structural health monitoring can help identify issues like cracks, corrosion, or deformation early, often before they become a serious problem. Now, during the life cycle of a structure, you usually have the design, construction, and operational stages. And it is in the operational stage where I believe structural health monitoring really shines, but it is not exclusive to. For example, in the construction phase, temperature gauges are often used to monitor concrete after the pour to inform engineers that it is all within allowable limits, or if it's not, then to be able to adjust in further pours and designs. In modern construction and high-value projects, structural health monitoring is becoming something that is planned for from the design stage, but you usually don't have that luxury with many existing buildings, especially as we have shifted towards a more reuse and recycling of existing structures as opposed to demolishing and building anew. To this extent, non-destructive methods help structural health monitoring and guide repair and refurbishment strategies. Why structural health monitoring is important, you may ask? Well, it's important because it provides critical insights into the condition and performance of the structures, ensuring their safety, reliability, and longevity. Now, structural health monitoring ties in with one of two main ways of structural maintenance and repair, which are reactive and proactive maintenance and repair. The reactive approach is where you let the structure sit and do standard maintenance until an issue arises, then address the issue, and then continue on with a likely now updated maintenance schedule. This then repeats until the end of a structure's life cycle, usually. The issue with this approach is that over time, the structure is left in a much worse off state, and it is much more expensive to do repairs this way. Where structural health monitoring really helps is with a more proactive approach, which reduces the likelihood of failures and helps extend the service life of structure, and over time significantly reduce the maintenance cost. And this proactive approach really helps with ongoing decision making, which can lead repairs to when, and more importantly, where it is needed. Now, the process of structural health monitoring involves several key steps to assess and track the condition of a structure over time. It begins with the installation of sensors, such as strain gauges, temperature and displacement sensors, or with various forms of NDT testing and inspections on critical parts of the structure. With newer structures, the installed sensors continuously or periodically collect data related to these changes, such as loads, vibrations, and other environmental conditions. This data is then sorted, processed, and analyzed using specialized softwares. Engineers then interpret these results and detect any abnormalities or signs of damage, such as cracks, excessive movement, or weakening materials. Based on this analysis, decisions then can be made regarding maintenance, repair, or even a continued safe use of the structure if it's in such a bad state. If structural health monitoring has not been considered at design stage, however, installation of permanent sensors can be very expensive, as often they would need protection from environmental factors and other installation considerations, such as if it is in for example, a foyer, you need to protect from people. This is where non-destructive inspection methods help by providing the need for periodic data collection to help assist with any sort of early detection of deterioration. As previously mentioned, the structural health monitoring has been something that has often focused on new or existing structures, and even in those cases, predominantly high value and critical infrastructures such as bridges, dams, tunnels, or high-rise buildings. As the shift towards reusing and refurbishing old structures is becoming more and more prevalent today, structural health monitoring is poised to enable the extension of service life for many of these old and even heritage structures. With these old structures, we are often doing reactive repairs and modifications to make them safe and repurpose them. These provide a prime opportunity for structural health monitoring systems and especially plans to be put in place so that the existing structure's operational service life is extended even further. By using structural health monitoring, maintenance and repair methods can be made more cost-effective over the long run and more efficient. Now, apologies. Now, there are several methods in structural health monitoring and that are widely used today, many of which are permanent sensors that collect data automatically. Today, though, I will focus more on the intermittent data gathering options, which can help with structural health monitoring of especially existing buildings, without having to set up any of the expensive and permanent data gathering devices. All in all, the methods I will talk about briefly today will be crack and join meters, drone cameras, LiDAR, which is light detection and ranging, thermography, ground penetrating radar, UPV, which is ultrasonic pulse velocity, UPE, ultrasonic pulse echo, and half-set potential testing. First up, crack and join meters. These devices come in in many different variations and forms, with the most old school versions kind of similar to the one you see on the image here. These devices are fixed directly onto a structure and measure the development of cracking and movement. They work by measuring relative movement between the two parts of the sensor. Modern and more expensive versions are usually installed with data loggers, and these are often able to transmit their data wirelessly without ever having to return to site. Generally, when needing to monitor multiple cracks, you will install many crack meters, as they only really record data at their installation points. So depending on the placement as well, they could be at danger of being exposed to the environment or other factors, which may compromise their longevity. Drones and LiDAR, which, as I said before, stands for light detection and ranging, have been one of the most impactful developments in structural health monitoring. I kind of combine these methods into one, as While they can be used separately, together they offer something that is, in my opinion, unmatched for assessing structures. Together combined, they provide three key things for structural health monitoring, which is efficient access, enhanced safety, and large area coverage. With their small frame, flight, and general mobility, drones' ability to inspect hard to access and not to mention dangerous places quickly and efficiently is unparalleled. Instead of a confined spaces rescue team, access, and engineers, the inspections can be just done with a drone operator and an engineer, which these days can be one and the same. With their cameras and LiDAR, these drones can cover large areas of a structure in immense detail that can either be reviewed as videos or even stitched together in full 3D maps where even cracks can be investigated. I've seen a couple of jobs where 3D drone mapping was used on this large structure where engineers had to count the amount of broken tiles in a roof section and actually guide the repair and maintenance plans without ever having to set foot on the roof. Now, the image you see here is from a job where a timber inspection had to be performed. And the use of drone here cut down site inspection time from 1 week to just a single day due to the speed and clarity the drone could achieve, not to mention the ease of access. No one had to wade across questionable timber joists and risks falling through the roof. With the clarity of the drone camera, excuse me, with the clarity of the drone camera, cracks, knots, and many other defects could easily be reported from the comfort of an office. Meanwhile, the LiDAR allowed for measurement and general survey of the area to be able to even count every timber rafter, post, and batten. Now, infrared thermography is a non-destructive imaging technique which helps to determine structural health. So this is a very useful technique to identify areas of hot or cold spots, which are associated with such defects such as delamination, voiding, cracking, and even moisture ingress. Infrared thermography can be done in a passive or active way, and is a quick way to be able to assess a structure through though it has several restrictions. Passive thermography relies on natural heat, so it has limited uses in areas where the structure is not exposed to the sun, or for some, and for the same reason, it is limited to what time of day it can be used. Active thermography, on the other hand, is where you apply an external heating source to the element to create a desired thermal contrast. Now, this method bypasses many of the restrictions I previously just mentioned with passive thermography, but it does have a much, much higher cost. Infrared thermography performed by drones equipped with infrared cameras is a really great way to quickly and efficiently assess large structures like bridges or even facades. Now, ground penetrating radar, they are a quick, easy, non-destructive way to inspect structural elements. These devices are often used to locate reinforcement within the concrete, but are also useful in identifying areas of delamination or major voiding within an element. When there is sufficient voiding, the signal actually will be reflected and be visible on the digital display. These devices are useful for all concrete elements as they come in many different sizes as well, so one can choose the best size for the job. The one major downside to them is the limited penetration depth, and this combined with the inability to see through metallic objects makes them a little inefficient in scanning densely reinforced and thick concrete elements. Now, ultrasonic pulse velocity measures the speed of transmission through any given element. It is suited for finding voiding within elements, as the speed will be slowed in any sort of voided or honeycomb materials compared to solid construction. This method is most suited for elements where there's access to both sides, so the transmitter and receiver can get a direct transmission for best results. This method is especially useful for detecting internal defects within columns, and I've actually used this to great success on a critical infrastructure project where the adequacy of a number of columns was questioned due to visible voiding on all adjacent columns which had to be knocked down. These additional columns that weren't knocked down, they simply could not be knocked down, as now there has been too much of a delay where knocking them down would actually pretty much delayed the project by 3 to 4 weeks. So we actually set up 32 test points around the circumference of a column across 3 slices, spaced 100 millimeters apart. And we actually found 2 areas where voiding could potentially occur and used comparative signal analysis to determine the quadrant where the defect was located. So with this method, not only were we able to detect a void within this column, but we're also able to guide repair procedures on site straight away by pinpointing the exact location of the voided area so that it could be drilled and subsequently repaired. In the end, the culprit was a fallen reinforcing chair from the column, which got suspended into concrete. And as the concrete settled, it kind of held up some of the aggregates, thus creating the voiding. Now, ultrasonic pulse echo is another method that is very well suited to the detection of voiding and delamination. It works in a similar way to UPV, but it has an array of transducers and receivers so that when the signal is sent out, it'll be bounced back and received by the rest of the array. This produces an image that you can kind of see here. This method is relatively quick and exceptional at finding defects in real time, though it requires an experienced operator to interpret the results as they can be affected by many factors such as vibrations. I've used this technique on site to scan large tilt-up walls which are cast on site, and the clients were worried about a strip bore in between these tilt-up walls because they suspected the vibration and compaction wasn't exactly done properly. This method was actually able to quickly spot voided areas within this bore. And due to the real-time analysis, advice on the condition of the element could be given with minimal turnaround time, making it an excellent real-time structural health monitoring method. Now, another method, with half-cell potential, it works by measuring the electrical potential between the reinforcement and a reference electrode. This method is not entirely non-destructive as it requires a connection to reinforcement, but it provides valuable information over a large area. This method does not tell you the extent or rate of steel corrosion, but rather the potential for it. With this method, you can create a potential map whereby you can see areas of highest potential and lowest potential of corrosion. This method greatly helps with the proactive maintenance approach, as we talked about earlier, as the potential maps can be used to direct destructive investigations as well as maintenance strategies to the most likely areas of deterioration. Half-cell potential combined with some resistivity measurements also help greatly with service life modeling for a structure. Now, a perfect showcase of structural health monitoring systems were present in a Southern Highlands redevelopment I've had the opportunity to work on. This was an over 100-year-old heritage structure that has been neglected and subsequently abandoned over the last 30 years. This decay meant that as a structure stood, it was unfit for operation with many of its structural elements in a questionable condition. In a perfect world, structures like this would undergo constant structural health monitoring with automated systems, but being a heritage structure, these were not a possibility. To minimize damage done to the heritage elements, a variety of non-destructive testing methods were used to assess the condition of the various materials in the structure, namely concrete, steel, masonry, and timber. All these techniques would be applicable not just for the initial investigation, but also for any subsequent ones as well, where these non-destructive techniques really shine is they are quick and efficient, and but they do require some specialist skills in data interpretation. Okay, so with the concrete investigation, the vast majority of the concrete elements in the structure were visibly deteriorated, but with mold, staining, and graffiti, the extent of it was really hard to determine at a glance. Due to the age of the structure and being abandoned for years, it had actually limited structural drawings. So For this, ground penetrating radar was used to determine the reinforcement cover over large areas of the concrete slab. This testing also picked up large areas of delamination in areas where water was able to pool. Destructive methods like strength and carbonation testing were then able to be conducted to supplement this non-destructive data. Now with steel investigations, the story was much the same. Half-cell potential testing conducted over a large area of the concrete slab and beams identified areas of very high potential corrosion. With the data gathered, potential maps were then created to be able to easily visualize on direct destructive conformations. It was found that most areas of concern were actually heavily corroded and lying in carbonate concrete, likely due to previous industrial use and neglect of the structure as well. Most of the exposed steel columns and beams were visibly corroded. Ultrasonic thickness testing was used to determine the section loss within the web and flanges of the members. Traditionally, drill testing, cleaning of corrosion, and physical measurements would have been used to gather this data. But due to ultrasonic testing, though, it was able to be completed in a fraction of the time. It was found in areas of wetness, 70% of the steel beam flanges are actually corroded and significant thickness loss was occurring on the columns located within this old industrial area. Now with masonry investigation, so the structure was predominantly made up of a masonry exterior with walls and columns reaching 4 stories. Ground penetrating radar testing was used throughout to determine the wall thickness and confirm the existence of cavities. As seen in the image here, GPR scanning detected 3 courses of bricks, and they were, you can see, separated by the red lines here. The speed and efficiency of being able to just ground penetrating radar scan a masonry wall to gather these information about courses and cavities meant that destructive drilling could be minimized in this heritage building, speeding up investigation works. Drones were also used to assess the condition of the masonry in areas that were hard to reach, thus also cutting down on even further time and cost. With timber investigations, at accessible areas, some readings were taken to determine the moisture contents of some of the timber posts. But due to the abandonment of the structure, the roof fell into disrepair over the years and exposed the underlying timber rafters, joists, and floors to excessive moisture. These were drones and LiDAR proved the most useful. With the rotten flooring, it was deemed very dangerous to actually access any of the upper floors. Without drones, erecting expensive and time-consuming scaffolding would have been our only option to inspect the structural timber elements at the upper levels. Instead, just a drone recording and scanning via LiDAR was able to get all the data that was needed to grade all the timber within the structure. To somewhat summarize, I would like to actually talk about all these structural health monitoring techniques and methods covered in the context of reactive versus proactive structural health monitoring. While in an ideal world, monitoring systems would be installed in every new and renovated structure due to the cost limitations, that is not entirely realistic. As many aging structures near the end of their original design life, proactive structural health monitoring can play a crucial role in significantly extending their serviceability. With various non-destructive testing techniques, regular non-intrusive maintenance procedures can be performed quickly and efficiently. Compared to permanent sensors, which can be intrusive and expensive, detailed investigations can be undertaken with new innovative approaches. For example, many old apartments, especially around Sydney and water, are showing signs of aging, from deteriorating facades to spalling balconies. In cases like these, drone imaging and infrared thermography can identify defects without ever needing a step through a residence. Ultrasonic pulse echo can identify voiding or cracking in a compromised concrete slab, while half-cell potential testing can identify areas of high corrosion chance before any visible defects even appear. These innovations in structural health monitoring, I feel, help significantly extend the service life of a structure by detecting issues before they become relevant and help inform maintenance strategies. So in conclusion, there we go. So in conclusion, with the increased accessibility of non-destructive testing and methods, non-destructive testing methods such as drone surveys, ground penetrating radar scanning, and ultrasonic pulse echo testing, and others, structural health monitoring is no longer limited to modern or high-value building. Asset owners should recognize that structural health monitoring is now a viable option even for older structures. Whether it's an apartment complex or a 1980s office block approaching the end of its 50-year design life, these techniques offer a fast and cost-effective and efficient way to detect and address any serious defects, ultimately helping efforts to extend the structure's design service life. Thank you very much.
Okay, thanks, and thanks, Mihaly. Beautiful. I'll just take remote control back. And ladies and gentlemen, I ask you to join us in thanking Mihaly for a very interesting presentation. The next presentation is by Aden Petersen. And a few words about Aden. Aden is a senior engineer, digital and spatial with Duratec, specialising in the integration of innovative digital technologies for infrastructure asset management. His experience in geographic information systems, business intelligence, and digital transformation in defence, government, and construction. He holds a Bachelor of Civil Engineering and is completing a Master's in Geographic Information Systems. Ladies and gentlemen, please join me in extending a very warm welcome to Aden Petersen.
Great. Thanks for the kind words, John, and thanks for your presentation, Mihaly. Mihaly actually touched on a few topics which I'll delve in a little deeper throughout my presentation. So, like John said, good afternoon. My name's Aden Petersen. I'm a senior engineer at Duratec, specialising in spatial and digital solutions. Before we jump into the presentation, I'd just like to quickly share my unconventional journey to this role to Duratec. My career began actually in the military down in Canberra, where I was studying civil engineering at ADFA. That led to my commission in the Royal Australian Engineers within the Army. And while I expected a traditional military engineering path, my career pivoted to geospatial intelligence, or GeoInt for short. Over the next decade, I worked with spatial data and intelligence, from analysing satellite and drone imagery for operations in Afghanistan and Iraq, to serving as the GeoInt specialist with the United Nations in South Sudan. Following my military service, I moved into the private sector as a Power BI developer and data specialist, delivering critical national projects for the Australian Electoral Commission, Treasury and Defence. This work focused on transforming complex data into simple, actionable intelligence for key stakeholders. Joining Duratec marked my return to engineering after 12 years, bringing a unique combination of engineering fundamentals, spatial data expertise, and experience in digital solutions. I feel like this diverse background allows me to integrate my alternative career experience with traditional engineering practices, which I've seen over the last 2 years. And today we'll explore how Duratec is revolutionising digital innovation, focusing on our flagship project, the National Carillion, as the case study. You'll see in this presentation that technologies aren't just preserving our past, but actively shaping our future too. So yeah, let's dive into the presentation. There we go. So today's journey and this presentation will be simply there. It's a discussion covering 4 main areas, one being the Carillion project overview, our digital innovation approach to how we dealt with this this project, as well as our innovation in action, how it was implemented, and then I'll talk about some of the key lessons learned to do with digital processes, machine learning, and photogrammetry. The intent of this presentation is to demonstrate how 3D modeling and data integration have transformed traditional engineering and construction practices. So just to give you a bit of a context, the National Carillon is located down in Canberra. It was built in 1970 and gifted by the UK or by Britain for Canberra's 50th anniversary. It's actually a musical instrument that houses 57 bronze bells. When Duratec was tasked with refurbishing its aging facade, Duratec's technical team, which is now MEND, realised this wasn't just another concrete restoration project. It was an opportunity to demonstrate how digital innovation could transform traditional construction practices. This heritage project became our testing ground for technologies that are now revolutionising how we approach other infrastructure asset management across Australia. And it'll be the base study of the case study for this presentation. Okay, so before I show you the digital solution that was created, let me paint a picture of what we typically face on a complex project like Carillon. Imagine trying to track 600 plus individual defects across a 50-metre heritage structure using traditional methods. You've got manual data with clipboards, pen and paper. You've got fragmented file structures spread across multiple systems. And then you've got the physical drawings that become outdated the moment conditions change or that they're printed. And then finally, you've got endless email chains trying to coordinate between consultants, project managers, site teams, and the list goes on. On the Carillon, this traditional approach would have meant scattered information, impossible real-time collaboration, and then weeks lost in documentation, validation, and administration. We transformed this, which I'll walk you through now. This is our digital solution, as you can see. At the heart of our approach was an integrated digital ecosystem. We combined 3D modeling, AI-assisted defect identification, and cloud-based collaboration tools. And this comprehensive solution created a single source of truth for all project data, from initial surveys through to final reporting. The 3D model, as you can see in the middle of the image here, was actually that central point of truth in which everything was either fed into or used as an output from. There we go. Okay, the power of 3D modeling. 3D modeling became our foundation for the Carillon project. Typically, we capture 8,000 to 10,000 high-resolution images to create sub-millimeter models. However, on the Carillon, we inherited a data set from previous work, which had about 1,100 images. This wasn't ideal, but it taught us some valuable lessons about adaptation. We created a hybrid solution, combining this digital model with our physical inspections. This model became the central data repository. Just imagine having every defect, every repair approval, every photo, all spatially located and accessible instantly to whoever has the link. For a heritage structure like the Carillon, this level of detail and organisation was game-changing in the way we communicated and was able to visualise this project. As you can see here on the image, we've got the model created from the drawings, a BIM or a SketchUp. We then used those 1,100 images that we inherited to create this reality model, which was then overlaid. And then we used it as a basis for all our other information. This one here is the existing Drummy survey, which we transcribed from pen and paper in some of the archives onto the 3D model. And then you've also got, you've also got purple layer here, which is the defects which were identified and placed onto the model. With the 3D model in place, we needed an efficient way to document and manage these defects, and this is where our digital workflow really began to show its value. So I'll just talk through how MEND, that's, as I mentioned before, that's Duratec's technical division, transformed the Carillion project delivery. Coming onto this project, we faced a massive challenge. We knew there was going to be a lot of defects, and there was about 600 defects that required comprehensive tracking from identification through to final repair and everything in between. And each of these defects needed multiple QA documents and PDFs. Using traditional methods, this would have been an administrative nightmare. And instead, we implemented the AnnoView 3D platform as our central source of truth. We then integrated it with Power BI for live project metrics and created custom automation that revolutionized our workflow. The results speak for themselves. It's an estimated 300% increase in QA report generation speed, and we saved approximately 70 hours through automation alone. But this wasn't efficiency for just efficiency's sake. It freed up engineers who would normally be doing these tasks to focus on complex heritage conservation challenges that required that human expertise and human in the loop. And whilst, to be honest, it wasn't all easy. I want to be honest about our digital journey on the Carillion. It wasn't without challenges. Inheriting this imagery, which is generally below our own capture standards, which we capture ourselves. There was a lot of shadows and uneven lighting with these images. So this restricted AI-assisted defect identification. As a result, we actually needed to do 100% physical inspection of the Carillion itself rather than our preferred AI-first assisted approach. That's the lesson. We adapted. We developed a hybrid workflow that maintained digital documentation benefits despite some of the data limitations. The comparison table here on this slide shows some of the improvements we achieved, even with these constraints and having to work through the hybrid model. At a 40% time reduction in defect documentation, we had instant access and self-serving information that replaced file searches. So although we didn't AI detect these defects, they were input into the model, which was real time. And then there we've got a 78% time savings in reporting. So I suppose the critical insight there is early technical team involvement from project inception ensures optimal data capture and then unlocks the full potential of digital workflows. If that technical team or digital team comes in the last couple of weeks of a project, everything's already been set and it's very hard to move within those parameters. However, if the digital team's there from the get-go, they can optimize those digital workflows. Digital defect management. So this kind of system revolutionized how we handled complex restoration. Our teams would go on site using iPads and laptops to record defects in real time directly into the 3D model. You can see kind of a screenshot in the middle of the screen there. That's the screen capture of the iPad screen. As they identified it when they were on the mask climber or cherry picker, they were able to snap a photo and input those details. Once that information was into the 3D model, engineers in Sydney could then instantly see updates from the site in Canberra. or across Australia for that matter. And then our consulting engineers could then preview, and sometimes they did approve defects, defect repairs without having to actually come to Canberra. That's a huge administrative burden which has been lifted, and a lot of savings in time and in the end dollars. For heritage, for heritage project where every decision needed careful consideration, this real-time collaboration was invaluable. And yeah, like I mentioned, we did save that 30% in admin hours and 40% in decrease in email communications just by having that model. Next, I'll show some of the images. So while the guys or myself were up on these mast climbers or cherry pickers to identify a defect. So you can't really tell in this photo, but this edge needed a full repair down the length of it. This is identified and a photo is taken and it is placed into the model. That model is then spatially marked in the 3D platform online, which anyone can see. This and then informed those contractors and engineers on where to repair it, with the final product being here, with this image also being uploaded to that specific location and that specific defect in the 3D model. Here's just a bit of a video showcasing that. So this link could be sent to anyone who needed or required access. You can see there's the layers can be turned on and off. That's the reality model. I mean, the quality is still quite good, and you can see that crack on the edge there in the middle of the screen. Defects have been turned on, and you can see that that blue mark, all the details are captured. The photo is then uploaded, and this is all from the iPad. And you can zoom in to kind of see the level of defect that it is. Details, as well as the QA and QC reporting, is also located and spatially located with that defect. With this project, there was about 600 identified defects, which were then mapped into this 3D model. So automation. So that model was our central point of truth. And from that, we used automation. Automation transformed our QA process on the Carillion. Previously, engineers were doing about 15 to 20 QA reports daily, which was the standard. The automated system, with all that data that was in the central point of truth, we were generating about 60 reports in 1 to 2 minutes. So just let me put this into context. We had about 600 defects on the Carillion, each requiring documentation at multiple stages. We had identification, breakout, repair, heritage finish. We're talking about thousands of individual reports and PDFs here. A custom Python script was developed and saved approximately 70 hours across the 9 facade reports alone, final facade reports alone. This 300% increase in generation speed and 78% reduction in processing meant that we could focus our expertise on some of the more complex heritage challenges rather than repetitive documentation. On the screen there, that's some of the code that was used. It's simply Python code, and then this is the PDFs that were outputted as a result. While automation dramatically improved our reporting efficiency, we needed a way to visualize and also track progress. And this led us to partially implement, if it works, business intelligence. So during the early stage of the Carillion project, we implemented business intelligence dashboards that provided real-time visibility into our progress. So just imagine stakeholders from National Capital Authority to project managers to site teams having instant access to defect counts, repair progress, and resource allocation. This this cuts out most of email traffic on a site, as you can probably imagine. While the full implementation was brief due to the project priorities, it was estimated it's demonstrated significant potential. There was a significant reduction in admin hours and the 40% decrease in project status inquiries. The self-service nature meant stakeholders could find answers instantly rather than having to wait hours for a response. For your information, these links can be accessed via just a link via your phone, iPad, or laptop, and all of these filters on the screen here can provide that self-service nature. So instead of having to ask about facade 9 during these dates, whether it's cracking or not, the individual can sort these out themselves. So yeah, this transparency and immediate access was really game-changing on this project during the initial stages. This is an overview business intelligence dashboard of the project itself. We were also using it for, yes. Yeah, that's perfect. Just quick, and just one more back, John. Perfect. So that dashboard there was just a bit of an overview of the project and some of the defects that could be seen through it. Next, John. That was a cost estimation dashboard based on various factors. And then next one, John. And then we were also using that information from that central point of truth to again forecast some of the timings for future works. Next slide, John. I'll quickly go through this due to the interest of time. We were using a combination of a server-based system and cloud-based. We found that cloud-based offered some real-time collaboration and just an increase in administrative hours and administrative acceleration throughout the project. Version control was automatic, and also using those online cloud platforms allowed direct linking into Power BI tools for live dashboard updates. Slide, John. And you can play this video. So the Carillion work connects to the future of infrastructure management. As you can see in this video, we can integrate many different data layers. You've got the 3D model from the BIM and SketchUp. You've got the historical survey data. You've got current defect information, which you can see with the photos and measurements. And this is an all-encompassing, comprehensive digital representation. Whilst we didn't implement a full digital twin with the Carillion, it advanced our 3D modeling groundwork, which was crucial. Next slide, John. So digital twins, as Mihaly mentioned, combine 3D models with sensor data and real-time information. It enables predictive maintenance and proactive planning. And just imagine having the Carillion, like if you had the Carillion with sensors monitoring concrete moisture, temperature fluctuations, and structural movement, as well as that integration with the defect data and maintenance history, you have a pretty complete picture of what's happening to that structure. This technology is becoming mandatory for large infrastructure projects in Europe and the US. However, for heritage structures like the Carillion, this could mean preserving our cultural assets through predictive maintenance rather than doing reactive repairs. Now that I've shown and talked you through this Carillion example and heritage project, I'd like to talk you through how it can be used in other construction and engineering projects. And here are some of the examples of past projects. John, could you just jump back two clicks, please? And one more. This is a power station chimney, which we modeled the external of. Next click, John. We also did the internal structure of this chimney stack, so we can see both inside and outside for that kind of inspection. Next slide, John. This is a really high definition version of a reality capture that we did. And next slide, John. It doesn't have to be a high definition reality capture to get benefit out of spatially located defects or digital defect mapping. Here's a good example where we've got a SketchUp or a BIM model, and we've spatially located those defects around it, just to give some kind of sense of where they are on a structure. Next slide. So machine learning represents kind of the next evolution in our defect detection lifecycle. The Carillion project taught us some pretty valuable lessons, and we did progress from manual visual inspections to our current hybrid approach with digital documentation. The future definitely lies with AI-assisted defect identification using that high-resolution imagery. And I think with high and proper data capture and those 8 to 10,000 images I mentioned, we can definitely train algorithms for pattern recognition and early deterioration detection. The implementation requires consistent lighting and quality training, and the projected benefits are significant. You've got reduced inspection time, enhanced accuracy, and earlier intervention with our preventative maintenance there. Next slide, John. So lessons learned and kind of the future direction. So whilst the project and the heritage case study there taught us some critical lessons about digital transformation, we know that high quality initial data capture is fundamental. It unlocks AI potential and ensures system effectiveness. Our hybrid approach did show that even with imperfect data, we can deliver 30% reduction in inspection time and enable those instant engineering reviews. So we did get quite a lot of benefit out of it. The integration between our 3D model and automation saved weeks of work. And looking forward, I think AI-assisted defect detection using that high-resolution imagery will represent kind of that enormous potential. The key is starting this digital journey now, learning from projects like the Carillion and building these capabilities into the future. So thank you for joining me today and listening to my presentation on the Carillion project. 3D models serve the foundation for digital workflows. But yeah, again, as I mentioned earlier, success requires that early technical involvement and optimal data capture. So yeah, thank you. And if there's any questions about the digital journey, just let me know.
Okay, great. Good. Thanks. Thanks, Aden. Just great, ladies and gentlemen. Jonathan, thank you, Aden, for a very informative presentation. I now invite both Aden and Mihaly to turn your microphones and videos back on again. We'll move to questions. Mihaly, just a question for you on the structural health monitoring, and in relation to the cost of the initial installation, especially in new builds. With regard to the cost of getting the new build projects over the line, very often the price of new structures and new build construction cost is very sensitive to designers and architects and engineers and developers, and they do everything they can to get that price down to within a budget. Given that structural health, the installation of structural health monitoring for preventative and proactive maintenance campaigns is going to have some element of cost there, how can we convince developers and architects and engineers to make provision in the original design, at design stage, for installation of these systems? Is there strong arguments to convince them to spend those extra dollars at initial spend?
It's a bit of a tricky question, right? Because as you said, they try and minimize costs as much as they can. So you kind of have to come at them with an approach of, uh, here's your cost right now. Sure, you may be cutting the price down currently, but over time, you have to kind of stress how much more expensive if it's going to be anytime something fails. And I think that's the best way to kind of point it out. The issue with that is that a lot of these assets often exchange hands. So yeah, it's a bit of a tricky one right there, honestly.
Yeah, yeah, and just a comment on that too. Very often, the people that build the structure aren't going to be the ones that are going to be responsible for the maintenance of it. So,
Yes,
in
yes.
maintenance, future maintenance often doesn't appear on their agenda. So, it's an interesting question for us as a society: is how do we uh, entrance that into the building and design process? Because it's definitely something that's worthwhile. It definitely does lower the overall cost of the project, but it's a question of how do we account for it in initial construction costs.
Yeah, yeah.
That's a challenge for us all to address, I think.
Mm.
Yeah.
These may have to be some things to probably be addressed in, maybe some sort of policy, incentives that, hey, if you're installing these, it'll be good for the future of the building. So for all those current builders and um, engineers, there should be some sort of like policy. I'm not a policy expert by any means, but anything to kind of steer them away, like, hey, this is a good thing to do for the future. Here's a bit of a incentive to think about it, sort of deal.
Yeah, great. All right, Aidan, a question for you, which has been asked by Novia, has asked, how did the defect capture in the first place? And speaking about the Carillion, um, was it by drone image or run by AI or manual tapping and then transfer to the 3D model?
Yeah, I'll answer that. So initially we were hoping to do a full AI detection or defect detection on this. However, with the images that we inherited, we had the 1100 images. It just wasn't there in terms of quality to do run those AI detection models over it. So that's where that hybrid model came in. We had that, I say, lower level resolution of the Carillion itself, but we had to manually physically inspect 100% of the structure. In saying that, we weren't taking it on pen and paper. We were inputting it directly into the iPad, into the laptop. So while it wasn't as efficient as we'd like, it still was we did introduce significant efficiencies into the defect identification process.
Great. Okay. All right. And ladies and gentlemen, I'll ask you to join with me. Oh, hang on. One more question has come in. And there was another follow-up question from Novia, and that is, how long does it take from inspection transfer to 3D model for the chimney project?
Yeah, so it takes, we generally say 4 times. Let's say there's a capture and it takes 1 week or 1 day. It normally takes four times that in processing time for a 3D model to be uploaded onto the servers or online. So that's generally what we work with. You can gain some efficiencies here or there, but that's the general rule of thumb.
Great. And ladies and gentlemen, I ask you to join with me in thanking our two speakers, Aidan and Mihaly.